extreme values of functions. So extreme values are maximum and minimum values. Of some function f. So when we're talking about extreme values, we're talking about a y value. So maximum, what's the biggest y value that we see? Minimum, what's the smallest y value we see, right? And a particular function I wanted to look at, a few actually. I don't have time for one or two today. Let's go to a new GeoGebra screen. Let's look at 3x raised to the 4th power plus 4x raised to the 3rd power 12x squared plus 2. And the reason I want to GeoGebra here is because it's easier to scale the axis with this Move Graphics tool here. So I can just grab a hold of the y-axis and say, hey, let's zoom out on just y. So there's my function. So as far as extreme values go, I've got this low point here, I've got this high point here, and this low point here. And so hopefully you remember looking at these in college algebra, pre-calculus class. You played around with a graphing calculator to find these extreme values. Now, some things to consider, there is no point lower than this one down here, right? There's nothing below that. The function looks like it climbs forever on the left and climbs forever on the right. So although there is a lowest value, this function has no highest value. It keeps going up and up and up and up and up. And we could just use our zoom out tool to kind of see that it's just going to keep climbing. And I can play around with the scale. And if I kind of really zoom out on this thing, let's use that scale, that set of dimensions there. When I really zoom out, this looks very parabola-like. So even powered polynomials, right, where the highest power is even, tend to have this U-type shape when you really zoom out on. When you zoom back in, right, there could be some interesting behavior going on. Let's see, the reset button. There we go, reset. When we zoom in, we can see there's some more interesting behavior going on in here. So we're going to learn to use calculus to analyze this interesting behavior. So if I just kind of use that function as my example, it drops down, comes back up, drops back down, comes back up. Like that right there. So this is my estimate there. F of x equals 3x to the 4th plus 4x cubed minus 12x squared plus 2. And as far as maximum and minimum values here, I have this point down here, I have that point there, and this point here. And the classification of these, this one at the bottom here is called an absolute minimum because there's nothing below it. It's absolutely the minimum y value on that point. Now, because this function climbs forever on each side, right, if we looked at the limit as x approaches infinity of f of x, we're going to find, hey, that also increases forever. Right, so that in behavior there and over there. There is no absolute maximum. So if you tell me, like maybe you say that y value there is 3, that's the 3 is the highest y value ever. I was going to say, no, there's a 4 and there's a 5, and way up here there's a billion. We keep having higher y values. And if I said the billion was the highest, you could go, no, look, I can get to a trillion. And we can just keep getting higher and higher. So these other 2 points, they are important, right? There's an interesting change here and here. These are called relative. So that would be a relative maximum, and this would be a relative minimum. Some definitions for like absolute here. So I would have an absolute max, let's say at, let's just call that x equals c for now. If whatever that y value is, f of c, if that's less than every other y value for x in the domain of the function, the domain of this function is all real numbers. So for any other x value in existence, what we're going to find is that this, when we plug that x value in and find the y value, so this is like our y1 and our y2 here, we're going to find that this y1 is always smaller than every other y value, no matter which x value you pick. So the idea here is an absolute is over the whole domain of the function. Now, a relative is a little bit different. So these relative ones, this is only the maximum if I just focus on like that region right there. So if I just zoom in and look at only that region there, in that span, that right there is the highest y value. So relative, definition of that, so we would have a relative max at x equals c if f of c, the y value, is less than or equal to any other y value for x in an open interval. Around whatever that number x equals c is. So if we pick on that graph for a second, here, if I were just going to zoom in here between like -1/2 and 1/2, as long as I just focus on that region, throw a couple of lines in there, x equals -1/2, x equals 1/2. So as if I just focus in between these 2 bars, that right there is the biggest point in that interval right there. And it is important to pick an open interval as opposed to a closed interval, so I want to explain the difference between those 2. And you should definitely read the book on this. So open interval versus a closed interval. So an open interval, it would be something like going from -1 to 1 in parentheses like that. So what I'm saying there is x is less than 1 or x is greater than -1. And when we read one of these, we read from the variable always. So reading from the variable, the way I read it, and I could read it the other way, I could say x is greater than -1. And I said or, but I should have said and x is less than 1. And if we look at that number line wise, over here is -1, over here is 1, and this one says x has to be greater than 1, -1. So that would be open circle at 1, go that way forever. This one says open circle at 1, go left forever, and means I want where they meet, and they meet here in the middle. So that's this interval right here. Question: what is the largest x value in this interval? Any thoughts on that? Something, yeah, Kelsey nailed it. Something incredibly close to 1. And that's the problem, right? No matter how close to 1 we get, somebody could get closer. So maybe I say, all right, Kelsey, this is it. It's 0.9999999. Okay, I'm tired, I'm done. That is the largest number in this interval. And Kelsey comes back and says, ha, I can get closer, right? And then Evan says, no, I got closer, right? And Abigail says, no, 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 I'm closer still. And Lorena says, no, I win, it's that one, right? And Cole says, no, no, it's this one right here, right? We can keep getting closer forever. So if there's an open interval, there is no max or a min guarantee. For an x, it absolutely doesn't happen. For the y values in a function, it can. So if I was looking at y values in an open interval, so I'm on this open interval for x, and then my function passes through that interval something like this, I can say, yeah, there is a max right here in that interval, but because the interval is open, there is no minimum because we can never get exactly to that point. With a closed interval forever, like if I go closed interval -1 to 1, right, that means x is less than or equal to 1 and x is greater than or equal to -1, then I actually get to 1 and -1, right? So in that case, if we had that same function here passing through those 2 points, and the points don't have to be on the axis. In this case right here, I definitely have a max right there, and the min is either this point or that point you pick, right? So if I'm on a closed interval, I'm guaranteed a max and a min. If I'm on an open interval, I have no guarantees. So that's an important distinction. All right, we are unfortunately out of time for Fun with Math today. Well, we'll pick up this discussion tomorrow and look at some other functions and see how calculus relates to these ideas of absolute and relative maxes and minimums. In the meantime, try and finish up that homework on differentials and message me if you have any problems. Thank you so much for playing today. Have a great day. Adios.